our next presentation, artificial intelligence and human industry software, theory and application in computer-aided engineering, will be done by Dr. Daniel Berger. Hello, Daniel. Nice.
Hi.
Even if online. He's a senior research engineer in the strategy and innovation team at Siemens Digital Industry Software, and explores the art of possible in artificial intelligence and machine learning, simulation, and quantum computing. So the floor is yours.
Thank you very much for the introduction. First of all, can you hear me well?
Yes.
And you can also see my slides. I'm sharing my screen already.
Yes.
Okay. Yes, only?
We can see you, not the...
you can only see me. Then I was in...
I will stop sharing here. Okay. Now.
Are you now seeing my screen?
Now it's okay. Now it's okay. You can see it.
Okay, perfect. Perfect. So first of all, thank you very much for the introduction and the giving me the opportunity to speak to you here. Well, first of all, it's very difficult to follow Hermann, and because he has such a deep knowledge about all the ways how you can combine engineering and artificial intelligence, and how you can use artificial intelligence to actually solve some engineering problems. But also, it's difficult because I don't know anything about you. I don't know anything about the audience, so it's a bit tricky to tailor a presentation for you. Therefore, I'd like to have it as interactive as possible. So if you have any questions, please interrupt me along the lines. Now, saying this, it was almost impossible to understand the questions from the audience. So if you have questions, it would be good if you have a microphone there. And I'm the first of a few people who dial in from at home or from their offices, so who cannot be there in presence. So it would be good to have a solution for receiving answers and then being able to answer them. So if you have a microphone set up, connected to your system, that would be great. All right, so let's start. Maybe first I give a little introduction to myself. So I'm Daniel. I'm not an engineer by training, but I'm coming from the natural sciences with physics and mathematics and chemistry in my background, and I got in touch to machine learning roughly 10-11 years ago during my PhD, where I was at the interface between physics and chemistry. But already there, machine learning was everywhere, trying to predict chemical reactions, trying to learn the physics, and trying to exploit the also experimental data that you have. So since I'm now in part of Siemens Digital Industry Software, I'm part of the technology innovation team, where I follow this line, and I'm very much interested in modeling the physics and exploiting data, using making the best out of the data that we have. And also, since our products, our simulation tools are very powerful, but sometimes complicated to use, one of my passions is also to enhance the user experience, to make the software easier to use. And that's sometimes coined as the phrase as democratization. I think I need to load my laser pointer. Hope you see that. Yeah, so if you like to get connected, you can scan this QR code and we can connect via LinkedIn. Yeah, so I'm part of Siemens, and Siemens is a huge company which is divided into several businesses. There's digital industries who address the needs of productization and product design, and then there's smart infrastructure, coming up with solutions for smart buildings. And then we have the business of building trains up to healthcare solutions, Siemens Healthineers. All of those different operating companies, or how you want to call them, they use AI. So AI is pervasive everywhere. Now, where Hermann and myself, and also a few others from the audience are here located in, is the Siemens software division, which is in connection to solutions where it's really about the hardware. How can we hardware and software within the factories, the motion control, also the process automation for the process industry. Yeah, so we are part of Siemens software or digital industries software, and this itself is a huge company. So it's 24,000 employees, and it's the market leader when it comes to digital software. We have many inventions, so patents, and thought leadership and coming up with new ideas is also in our DNA, and that's why we are happy to have this market position. One of the key visions that we have is that we want to connect the digital world and the real world wherever possible. And this falls into this regime where we think about designing a product on the computer, using software, using design tools to design a product, but then also observing how this product performs in the real world and connecting those two worlds, leveraging the data from the one side to improve the digital model, for example. This now also takes the second loop, where a big part is making coming up with a digital version of a plan, how you want to productize, how you want to fabricate, manufacture those products, having software to model this, having software to optimize the production process, but also observing how this production process looks like in the real world. And again, leveraging all the data that you can absorb, that you can measure along the lines in order to improve the production process. And you can see this as such an infinity loop if you think about generations of products. If you design a product digitally and you observe it, how it performs in real world, and then you go into this production loop, all the information that you gather, you want to use for the next generation of your product. So think about an iPhone. Obviously, there's coming a next iPhone in the next year or the year after. So you want to leverage and improve or make design decisions on all the data that you collected along those lines. So that's one of the visions that we have. In the segment that Hermann and Christy and myself and Razvan and Alexandra and so on are part of, we focus on simulation and test solutions. And one of maybe the main workhorse that we have is the SimCenter portfolio, which is a simulation and test portfolio, where we go into all the complexity of the model that you can think of. We explore all the possibilities, and here I mean simulating structural problems, fluid problems, thermal problems, electromagnetics, linking this to acoustics by test and simulation, and even going into the very small regimes of molecules, namely modeling the chemistry of some processes. Obviously, going faster is something that everyone wants to have. They want to have, our customers wants to have design decisions much faster. And a key element is that all those software solutions should not be isolated, but we need to stay integrated. Because in industry, in big companies, models is the key asset, models and data is the key asset, and that needs to be shifted around from one department to another department. Thinking about a model for a car, for example, this has to be consumed by the department who's doing the aerodynamics of the car, the test of the car, the design of the car, or thermal simulations, or the complete system simulation. So the important thing is that any software solution needs to be integrated along the possibilities of computer-aided engineering. Now, this was enough of advertisement, so to say, of Siemens Digital Industry Software. Now, I want to spend some time, and please interrupt me, as I said, to see that I bring the most value to this event as possible. I'd like to discuss, let's say, an easy approach to deep learning. There are many presentations following which start to already discuss neural networks, and maybe there are a few people in the audience who are not well completely, or have not so much experience with neural networks. So maybe it's a good icebreaker to think about how actually the complex neural network structures are actually quite easy to understand if you know where they're coming from. I want to then add some general overview, some comments on AI and machine learning that might be worth to share before I then go into presenting practical applications, use cases from my field, where it's about using AI to accelerate simulations, make efficient design exploration, and also enhancing the usability of software. First of all, also a little bit of definition. There are many different schools who have a different interpretation of what artificial intelligence is and what machine learning is, and whether are they overlapping or not. We've seen this picture by Hermann before. I now have only one circle where this is, or one ellipse. Artificial intelligence is everything which enables the computer to mimic some form of intelligence, or making seemingly logical decisions. Machine learning is a subset, which some people claim is very advanced statistics, but it enables the computer to learn connections. And deep learning is a subset of machine learning, where to some extent the computer is more powerful because it can do predictions without specific feature engineering. And this comes from the fact that typically neural networks are much deeper and have some invoke some tricks along the lines in order to make those being as powerful. I'm hearing now I have some problems. Someone has to mute the microphone. I'm hearing an echo. Now it's gone. Okay. Yeah. So from linear regression to deep learning, I want to make this very approachable, very easy. For some, it's boring, but for some, it might be worth thinking about this for a few minutes. So let's say we have a couple of data points, X, and Y, and you have the task to draw a line which in the best way represents these points, right? A line is something like this. And if you have it in more dimensions, let's say X is not one dimensional, but has many dimensions, then you can write this formula as this. And that's a very typical problem that all of you have faced, right? Either if you are looking at experimental data or in statistics, that's a very, very, very common and basic problem. This problem can also be pictured like this, where you have, here is the input data X, and now you see that this can be multidimensional. So let's say this is n-dimensional, so it's actually a vector. And you multiply this by those factors W, which in the future we're gonna call weights, the weights of the neural networks. And then you sum them up, add this little shift, which basically just shifts this line to the top or to the bottom. And then you can combine this and look at the outcome of this. So this is basically Y. And that's called the output neuron if you formulate this, or if you depict it like this. This is the input layer and this is the output layer. So linear regression, very easy. You want to find the line which is the best representation for the data that you have. You can measure how good this line is in a way that you calculate the error, and the error in terms of you calculate the difference between the actual data value and the value that would come out of if you evaluate this line function. And you would sum up overall the data points, which gives you the complete error, or how people from with a neural network background would call it a loss function. Now, if you have defined the loss function, you can do something which is called training. Namely, you evaluate a gradient of the loss function for each of those weights. And by this, you can optimize the weights to give a better approximation, or a better fitting line through the data points, right? So you can do this, and it's a loop. You would do this over and over again, improving the weights such they give the best representation of the data, or that they come up with a line which is the best a line function which is the best representation of the data. Now, let's say you don't want to get a line which is the best value to represent all of the data, but now let's say that you have two different classes of data points that you want to separate. So you want to find a line which separates those data points into two classes. That's a classification problem. Before there was a regression problem. You want to find a function. Now it's a classification problem. You want to separate those data points which fall into different classes. In this case, it would look easy, but let's say the data point would look like this. Now you have a hard time to find a line where all of the data where you have a perfect representation over. You cannot separate the green circles from the orange squares by only one line, right? You wouldn't find a line that would be able to do this. So you have to do something. You have to draw something which is nonlinear, an arbitrary shape. And if you do this, then you have no problem to find some kind of function which would separate those data points, or how we would call this is a decision boundary. If you are on the one side of this function, all the data points fall into this one class, and on the other side they fall into the other class. So that's the decision boundary. Now, in order to have this nonlinear function, we just do one trick. Namely, we add a nonlinearity, some arbitrary or some not arbitrary, but some nonlinear function that you would apply, that you would apply to this value that you have here. Typical candidates are sigmoids, but basically any nonlinear function in principle would do. You have a different definition of the loss function, or the loss function in principle stays the same, but you have to add this nonlinearity function here. The way how you calculate the gradient stays the same, and the way how you train your model stays the same. You just loop over all the data points, and then you loop over the data points, and that's called now logistic regression. Oh, I'm sorry for the typo here. That's logistic regression. So we went from linear regression to logistic regression by adding this non-linearity. And logistic regression is already the simplest form of a proper neural network that you can do. Now you can expand this. You can think of this by adding more intermediate neurons, which take some combination of the input values together with some weights, and you have intermediate or hidden layers, how you call them, where you calculate again the linear combination plus a bias, and then adding the nonlinearity. And you do this along the lines. And for training, you simply do the same. You calculate the gradient, loop over the data that you have, you calculate the gradients and adjust the weights in the neural network to give a best representation of your model. And with such a, let's say, more powerful setup, you can do things like, for example, image recognition. In this task, you wanna that's one of the prime examples that also very approachable if you want to do some learning on the internet, some machine learning course. They would always start with this example: handwritten digits, and you have to classify them into their different classes. Make the model recognize that this is a 7. You have a neural network like this in principle. It might be a bit larger when it comes to the number of neurons, but the setup in principle stays the same. For this example, the input layers, the input layer, the number of all the neurons within the input layer represent pixel values of this input. So this is the a pixelated version of you make a snapshot of a handwritten digit, and then you downsample it, make it very pixelated. Typically, you end up with 28 times 28 pixels, so very pixelated when it comes to digital photographs. But this already makes the neural network, the input layer, having quite some dimensions. But it's very easy to implement, and also it's also very easy to train, because you only have to do gradient descent. And the cool thing about many machine learning packages is that you have an automated differentiation available. And this the way how you make use of this automated differentiation is often called also as back propagation. You would back propagate the error that your current model has in your current instance, and you propagate so let's say you have a misclassification here. You would evaluate the loss and back propagate this through the neural network and adjust the weights accordingly. And this can be done very, very efficiently, and that is basically the reason why neural networks gain so much attention, because it is very efficient. It's a universal approximation of any function, so you can with a neural network in principle you can approximate any function that you want, and it's very efficient because you can, because of this back propagation, because of this automated differentiation, and make use of this in terms of the back propagation. Now, this is a neural network. If you want to go up to deep learning just means that you have a neural network with many more layers, which makes it more flexible. And then typically you also make use of some tricks like convolutions, that you have a convolutional kernel that you pass over the data that you have, and some other tricks. You can make some recurrencies in some internal loops within the neural network. I don't want to go into too much into details here, but it's very it's not much different from linear regression or logistic regression. It's just more. It has more dimensions, and you apply some tricks. But in principle, the things stay the same, and the way how you train the model is the same. The way how you use data is the same. Exactly. Now, one asset that deep learning has, it is by having those intermediate layers which do automatic feature recognition. So, for example, if you have those convolutional map, it implicitly learns gradients of the models, and if the next layer you can combine some of those features that you learn, like gradients, to recognize sub-features of the models. And at this point, it already does not matter where exactly in your picture you find this feature. It will make use of it in the final classification problem, or in the final classification step. So deep neural networks have the advantage that they have built in these kind of invariances. It does not really depend on where in the picture you find those features, but you recognize those features, and then later on you make the decisions on the fact that you have recognized those features. And that's an important step, because in this simple neural network, here you are still bound to the exact pixel values. So a 7 always have to start somewhere here, right? So that's here you work with the direct pixel values, and you have no feature recognition in between. Here, with the deep neural networks, by using convolutions and so on, you make use of that. All right. Again, the reminder, if you have any questions along the line, or if you say, we all know this already, then please let me know and I can adjust and talk about something else. Now, some things that I want to share with you, my view on important elements of artificial intelligence and machine learning. And some things obviously have been said by Hermann already, and I assume that some of the next speakers will refer to this as well. The first thing that is that's the most important thing is the data that you have. And when you think about the data that you have, it is important first to see whether it is labeled data, whether you have labels available. So if you have an image recognition problem, you need to know whether, well, if it's if you have pictures of a cat, you need to know the label of that's a cat, or and a dog. So you need to have labeled data. And this is often a problem in engineering, because labeling often does not come for free, but means needs human interaction. Someone has to label the data. So you have to distinguish between then supervised learning and unsupervised learning. An important thing, if you evaluate your data as well, is you have to look at the aspect ratio. And this is what I tried to show here. The dimensionality of the problem, you need to compare this with the number of data points that you have. And you really want to have this like a very thin column, that you have small dimensions, but a lot of data. Then you have no problem to train any machine learning model. And also, how many output dimensions do you have? Another important aspect is, do you have structured data or do you have unstructured data? Do you have, can you represent it in form of an Excel sheet or a CSV file with clearly defined columns? Or is it less structured and you might need to build a semantic model or some kind of data model which is a bit more advanced? It's tricky, but in some cases where you don't have enough data, You need to take this detour and come up with a semantic model to impose some knowledge into the data that you have. Then what is your output dimensions? Do you have 1D or 2D or 3D values that you want to predict? Do you have maybe a sequence that you want to predict? Do you have a time series? Or yeah, in general, a sequence, like if you want to predict, if you wanted to generate text, that's also a sequence, right? Then the biggest task is to mold your engineering question into one of the available AI machine learning tasks that you can get off the shelf, so to say. Do you have a classification problem? So do you need to separate your data points into different classes, and do you have labels for that? So clustering versus simple classification. Or do you want to predict values in terms of a regression? So do you want to learn a function which is able to predict values, and then is it 1D, 2D, 3D? Do you have a generative task that you actually are working on? So do you want to generate images, for example? Do you want to generate texts like in ChatGPT, for example? That's a generative model. Or maybe you just have lots of high dimensional data and you want to use a dimensionality reduction technique, or you want to convert your data. That's also something that can be done by machine learning. Or you want to do rule extractions and so on and so on. But it's important to, if you have an engineering problem, try to rephrase it in one of those tasks, because then you find lots of solutions how to do this. Once you have made the decision on what kind of AI machine learning task you have with your engineering problems, you can think about algorithms. This is a non-exhaustive list, obviously, because new algorithms are popping up. But maybe you can separate them into purely data-driven models, like most of the neural networks which are available, or support vector machines, decision trees, and so on, which are there for, let's say, static problems. But then you have something for sequences like Markov chains, recurrent neural networks, LSTM, or if you think about really foundation models, the largest models, the most capable models that you can think of, like ChatGPT. These are transformer models, transformers, how you would call them. If you have some physics available that you can inject through your data, you should make use of it. And this can be done through physics-informed neural networks or operator inference, solver in the loop, and the list goes on. New approaches are coming up regularly. Now, if you made the decision on the algorithms, you want to think about the model deployment. Where do you envision the machine learning model to be deployed? Will it ever be deployed? Is it only there to be used once to solve a certain question? Or do you want to reuse it in the future? Do you make it available for others? You can deploy it on the cloud. You can deploy it on premise. You should also think about, once you have more data available, what is your strategy to retrain the model? Hermann talked about transfer learning. That's a very important issue. How can you make your model adapt to a certain domain? And maybe you also have the possibility that you can collect data from many sources, and you can combine this data and ship out models, train the model. That's called federated learning, where you have data sources at many points. You're going to collect them and train the model and ship out the model again. And then something that should not be forgotten is the hardware. Where will the model be deployed at some point? what is what are hardware limitations? Do you have a GPU there to evaluate your model, or maybe only a very small computer or a chip with limited cache, for example? So you might think about how can you reduce the complexity of your model, and then you would end up with tiny AI, so very small models. And also, one has to think about power consumption of models. So, for example, you all know about ChatGPT and how cool it is and how what amazing things that you can do with it. But one needs to be aware that training such models is extremely complicated, and this also is true for the power consumption. So you really, or the people who trained the model, had to spend millions on electricity to train the models. That's how complicated those models is, and how complicated how power consuming it is to train with all the data that is necessary to make those models to a quality that is acceptable. I want to now talk a bit about a typical machine learning pipeline that you have, or that's the pipeline how I would see it. You start with collecting the data, and this comes from many sources, sensors, maybe from cameras with images and videos, documents, maybe it's speech input, maybe it's simulation results, simulation models, or simulation results. So there it is really up to you to come up with maybe also new data source, but at least use most of the data sources that you have available, combine them, and then a big first step is the data preparation to make it in a form that can be digested by a machine learning model. So this involves cleaning, and probably you lose most of the data that you have by cleaning already. Then you would split it up into a train data set and another part of your data set that you will use later on for testing the quality of the model. With the train, with the part which you want to use for training, you're going to train the machine learning model. And here, there are no limitations. Many models are available. Neural networks, Gaussian processes, random forests, to name only a few of them. Then you will end up with, you have a trained model which seems converged if you look into the training error curve, or the learning curve. Then you want to evaluate the model, namely you're gonna use your test data set to see how good it performs. Or you maybe have a test and a validation data set, and there you would use your validation data set. So this is model validation. And from then, if you are confident, you want to think about deployment to production. So you need to think about model packaging and the things that I just mentioned. Where do you want to deploy this? Bring this into a format which can be deployed there. There are more or less universal forms like ONNX formats where you can export, for example, a neural networks that it can be used in many forms, in many situations. Exactly. And then you have to think about what I was saying. Once you have more data available, you might want to re-enter this loop and retrain the model. But it's good to have a strategy already ready when it comes to the situation that you want to retrain the model. There are many models out there, but if you look at what are the machine learning models which are most frequently used, these are not the complicated models. And here I show you a picture from the Kaggle survey from, it's already a bit outdated, 1.5 years ago. I couldn't find the one from 2022. but I don't expect it to look much different. You see that the most common models, the models which are most frequent, are things like linear or logistic regressions, because they are very good for the first guess. Namely, when you explore your data, these are already very valuable approaches where you can quickly get some insights, where you can quickly see where you might have some redundant dimensionalities and so on. And they are cheap and interpretable. Then there is another family based on decision trees, and then some cool combination of decision trees, which are called random forests, or boosted decision trees, which pay a bit more of the attention during learning where the model does not perform well. These are also very, very, very cheap and always worth to apply to the data that you have. What I find problematic with them is they tend to overfit. They tend to learn too well the data that you show them, and then they might have a bit of a harder time to extrapolate. But yeah, everything depends on the data that you have. And then if you add complexity, you get to the convolutional neural networks, you see Bayesian approaches, some other kind of neural networks, which are just very, very long, complicated, dense neural networks, models for which make use of the history, or which are good for predicting sequences. And then those very powerful foundation models like transformers, they are increasing, they're getting more attention, but as I said, they are so expensive to evaluate that you will only want to use them once you have sufficiently explored the data that you have. So that's why I also went through this educational process of starting from linear regression, logistic regression, and neural networks, because these are so fundamental tools which are still frequently used by everyone in data science. I think I skipped this one. Yeah, now to some applications. And here there is some overlap with what Hermann already presented. I'm gonna talk about reduced order models and ways how to accelerate design space exploration. I think I have 10 more minutes, so I need to hurry up a bit. We've seen this picture by Hermann, and the only thing that I wanna say here is that there are different approaches depending on how much physics you're able to inject into your model. How much physics do you have available that can be used during the training or into the formation definition of the model? And some are pure data science. And well, there's not a universal reduced order model approach, but it really has to be evaluated for the data that you have, for the physics that you have available to come up with the newest one. And it always makes sense to train many of them and compare how they perform. If you look at a common KPI like fidelity and fidelity value of the model. This one has been shown by Hermann already. The important thing is that it combines the world of system simulations, where you can put together a real system like an air conditioning system in the car, and you can simulate this in terms of a system simulation model, where you can put together some very basic physics elements, and they simulate the asset that you want to simulate on this level. Now, these are already very quick simulations, but for things where you want to do design space exploration, where you want to evaluate how those models perform under various conditions, you need to evaluate them many times. And therefore, even speed up for those fast simulations is very important. So here is such an example for the cooling system within Tesla, and here the cooling system of the battery pack. Another example is not 1D simulations, but 3D simulations, where you make a reduced order model of here a thermal simulation of the battery packages. It is physically more sound information, so to say, that you have more from closer to ab initio. So really where you solve the physical differential equations to get the behavior of the system. You can make a reduced order model for this, and you are obviously much faster, because thermal models or computational fluid dynamics is so important if you really want to calculate this. Another example for internal combustion within an engine. And here are some parameters that you want to optimize. Don't have time to go into details, but it links now computational fluid dynamics to reduced order models for very efficient design space exploration. Now, one example that has been named before is physics-informed neural networks. This is an approach where you have a simple neural network, but you include knowledge of the differential equation into your loss function. And if you loop over the system that you want to simulate, unfortunately, this is not a video, but here you want to simulate the computational fluid dynamics in a cooling problem. I think it's a computer chip, something that you want to cool. You don't need data for this approach, but you just use the knowledge of what's the physics of the system, namely encoded in the differential equation. You make use of it when you evaluate the loss function, and this way this neural network will converge to give the physical sound prediction, because it wants to minimize the error coming from, well, the error that you typically have in a neural network, but then also the error coming from the difference to the differential equation. Maybe I jump this because it has been. I have 5 more minutes, so I hurry, and maybe go to reinforcement learning just very quickly, because that's not been covered yet. Reinforcement learning is a very cool approach where you have some kind of, we call it agent, which explores the environment to learn a sequence of best decisions, or a good sequence of decisions. And if you iterate it and iterate, it will come up with the optimal strategy, which is available within a certain environment. It has been applied to, you know, the examples from you can train a model to be very good in playing chess or Go or any kind of computer games, like also Counter-Strike. But you can also link it to simulation software, and you, as Hermann was mentioning, I have to jump to this one. You can also link it to, let's say, a system simulation, and you let an agent explore what is the best strategy to control the system here in the environment which is defined by the simulation model. Running out of time, it is also important to not looking into how we can speed up the simulation, but also how can we make engineering software more user-friendly. And one of the big challenges is, if you want to do a full CFD simulation of a car, for example, you know, it's an integrated software, so you typically are shipped the entire model and cut model of a car, which may involve 20,000 parts. Most of them are irrelevant for the result of the CFD simulation, but they require meshes to represent them. So you want to remove those small parts like nuts and bolts and clamps before you actually want to run the simulation. That's the preparation step that you have to do for simulations. And that can easily take 2 weeks if you want to run a simulation of a car, because you have to remove those tiny parts that you don't want to get captured, like screws and nuts and bolts. So we took the challenge and wrote a little cut recognition software, which would recognize those small parts that you want to remove during the simulation. A model which makes use of point cloud information, mesh information, and then also, if you make snapshots of the card, of the cut part, train machine learning models, combine them, and then make it classifying them into those parts which are useful for a simulation, which you want to remove. And by this, you can tremendously speed up this daunting task of cleaning up your CAD assembly before you can actually run the simulation. I want to stick in time. I have many more slides, but I think I want to stick in time, and also don't want to, I don't want to steal time from the next speaker. So I think I jump over the next topic, which would be recommender systems. One last sentence on, because Hermann was touching on it, is knowledge graphs. And I can only recommend everyone to get familiar with knowledge graph. It's very approachable. And here I'd like to draw attention to the open source software Prodigy. It's coming from Stanford, and you have a very nice tutorial how you can set up a knowledge graph, how you can define an ontology for a system, and then how you can make use of a knowledge graph. And this is basically only a concept where you define properties and relations between the data. And this is very powerful, because in engineering problems, you most often have the problem that you have the data is scarce. You don't have lots of data. You need to make the most out of it. So you need to inject domain-specific information. And that's why it's so important. And then later on, you can still do machine learning, but this is the part at the very beginning where you need to think about how you can make your data leverage in the most efficient way, and how you make it, how you can prepare it for machine learning as an input. And there it helps that you impose structures from the domain knowledge and relations. If you know about them, you have to inject them. And that's the way how you can do this. All right. With this, I would like to thank you very much for the attention. And if you have any questions, I think I'm running out of time. I went a bit over. If you have any questions, if you want to get in contact, please feel free to reach out. I'm happy to discuss. Thank you.
Yeah, but maybe there are some questions. Okay, maybe that question will come via the email.
Okay. Thank you very much then.